And I want to pick up our discussion from the beginning of Module 3. On Tuesday, we went through the hypothesis testing process, the steps that are involved. And then we talked about the difference between parametric and non-parametric tests. And we will be exploring some non-parametric tests in this course, which is new material. It's something that we don't cover in Stat 1401. But the other topic that we want to talk about that's in the first lesson of Module 3 has to do with normality. If you'll recall, when we talked about the parametric and non-parametric test, one of the assumptions we make whenever we're going to use a parametric test is that we have a normal distribution. We either have to be told that it's normally distributed, or we have a sample that's greater than 30, which then would allow us to apply the central limit theorem and force any unknown distribution to be normal. But there are some tests that we can conduct. If I were doing the research kind of in the real world and I want to know whether I have a normal distribution, I don't want to make that assumption. There are some tests we can do statistically to verify whether we have a normal distribution, and they're called normality tests. So we're going to talk a little bit about one specific normality test. Now, again, there are a variety, but we're only going to focus on one. So a normality test, again, let me get this out of the way, is used to determine whether our sample data has been drawn from a normally distributed population within some tolerance. I mean, we can't be, 100% totally confident that we have a normal distribution. So there is some tolerance. We can be like 95% confident or 99% confident that our sample data was taken from a normally distributed population, which then allows us to apply things like the normal distribution and a variety of other statistical tests that rely on the assumption that I have a normal distribution. And we're already hung up this morning. Let me get back to fix my PowerPoint because it's wanting to be moody. I don't know why it does that. Okay, so within our normality test, come on. There are lots of different statistical tests that we can run if we know we have a normal distribution. We can use things like the one mean Z test, the one mean T test, the two mean T test. We can conduct a one-way and a two-way ANOVA or analysis of variance. And we'll actually be talking about in this course, we definitely do the one mean T test, the two mean T test, and a one-way ANOVA. So again, for a lot of the statistical analyses that we do, we make that assumption. So really this test of normality is one that you almost have to run or conduct near the beginning of your research so that you can justify the assumption that it is a normal distribution. There are different normality tests. I saw a list the other day of about 4 or 5 different ones, but we are only going to discuss one of them. We're only going to focus on one of the normality tests in this course, and it's called the Anderson-Darling. And Minitab will create a graph and provide the appropriate statistics for us using the Anderson-Darling test for normality. So that's the one we're going to focus on. Again, it is not the only one that exists. It's the only one we're going to talk about. So Anderson-Darling is a statistical test to determine whether a data set comes from a certain probability distribution. Now, again, our focus is going to be on, does it come from a normal distribution, which is the most common type distribution that we want to consider. But Anderson-Darling could also be used to determine if the data comes from, say, an exponential distribution or a uniform distribution or a binomial distribution. But again, our focus for this course is going to be on whether it comes from a normal distribution. Again, because we have to make that assumption for many of our analyses that we do. So when we do an Anderson-Darling test, it's almost like conducting a hypothesis. You have to, it's sort of like the question would be, your research question, so to speak, would be, does the sample data come from, or was it selected from, a normal distribution? In other words, was the population that we used normally distributed? There's lots of ways to ask that question, but that's kind of the question that we're asking when we're looking at the data set, really before we do any kind of other analysis, because again, we have to make the assumption that we have that normal distribution before we conduct the test. So the kind of the question that you have to ask yourself is, does the sample data, was the sample data drawn from, taken from a normal distribution? Well, in an attempt to answer that question, you're either going to ultimately say, yes, it was, or no, it wasn't. And so your proposed answer to your research question, remember, becomes your hypothesis. The null hypothesis, again, remember, always contains equal in some form. So in this scenario, that would be like saying, yes, the data follow or equal a normal distribution. Okay, so the null hypothesis for the Anderson-Darling test is always stated, the data follow a normal distribution. And again, that's like, that implies that it's equal, that it's the same. The alternative hypothesis will always be stated, the data does not follow, because that's like saying it's not normal or not equal. So again, we haven't violated kind of the rules or the guidelines that I gave you on Tuesday about a hypothesis test. Remember, the null hypothesis must always contain equal in some form. And so using the words equal here is stated by saying it follows a normal distribution. The alternative is the exact opposite, which would be not equal, and the phrasing is does not follow a normal distribution. And then we're going to gather our evidence by calculating the Anderson-Darling test statistic. And in the end, we have to write our final conclusion. And we always write our final conclusion for any hypothesis is written as a complete, detailed sentence. And I have a template for how that sentence should read. For the Anderson-Darling test, it says preliminary analyses showed the data set for whatever the variable is or is not, that's the decision you have to make, normally distributed as assessed by AD. AD here, and hopefully it makes sense, but AD stands for Anderson-Darling. and P equals, and the P here represents the p-value. A lot of times you'll see we just use the letter P instead of writing out the phrase p-value. Okay, so that would be the detailed sentence. Now we have to add in the details by indicating what variable we are analyzing, as well as the value for our Anderson-Darling test statistic and the corresponding p-value. Also remember that I mentioned, I think I did anyways, on Tuesday, that each test statistic has its own unique p-value. Okay, so Minitab is going to give you that information. I do have the Minitab steps, the clicks you would use, okay, to calculate the Anderson-Darling, and we'll be going through those together here in just a minute when we look at an example. Okay, so they are on slide 5. If you want to, make a note, add them to your or have them all together on a sheet of paper. So we're going to take a look at some examples, and I have them on the PowerPoint, but again, I've taken them over to a piece of paper so that we can look at it together. So this question says, the Institutional Effectiveness and Strategic Initiatives Department at Georgia Highlands College wants to know if the ages of students in fall semester 2022 are normally distributed. A sample of all students in 2 different Stat 1401 classes at GHC are surveyed, and the results are provided. Now, the results are not provided on the PowerPoint slide, nor are they provided here, because you need the raw data. So I put the spreadsheet that you need for this problem in the lesson. So under Module 3, for hypothesis, p-values, and normality, if you look at that page, I have data sets for normality test examples. And so I have example 1 is the Stat 1401 class survey. Typically in my Stat 1401 classes, I do a survey to collect data that we can then use throughout the semester so that students get some experience using real, possibly messy data. And so these are the results for this semester. So it is in an Excel spreadsheet. So I'm going to click on it. I'm going to save it. Because it's in spreadsheet form, we have to copy and paste it into Minitab. And I think you guys have been doing that before. Okay, you should know how to copy and paste to Minitab. Give it just a second. It timed out on me. Okay, so then I've entered my data. I collect information from students just so you can see. I ask questions about their age, their eye color, pathway, county of residence, how many credits hours they're taking, how many hours they're employed, the month they were born, how many siblings they have, their race or ethnicity, their marital status, and then I go back and add their adjusted GPA. But the question here, let's go back to the question, says wants to know if the ages of students in fall semester are normally distributed. So again, if you want to think about it in a question form, okay, in question form, our question here would be, are the ages of GHC students in fall 2020 normally distributed? That's kind of the question that we're trying to answer. And it's not formally written out in a question form in that scenario, but again, that is the kind of the implication or the implied thing that we want to know. You're not required to write out that question when you're working through these problems, but again, I'm trying to help you see kind of what the question would be. So if we begin our hypothesis testing process, if you'll recall, step 1 in the process is to state the hypotheses. Remember, your hypothesis or your hypotheses is your educated guess or your proposed solution. So for this problem, and again, typically you'll see it written, remember H with a subscript of 0 will usually be on the top, and then H with a subscript of A is on the bottom. You'll usually see them stacked on top of each other. Okay, so you have, kind of think of it as 2 rows. So your null hypothesis is on the top row, the alternative is on the bottom row. And again, that's just kind of the standard that you see. So in this case, we would say, and you could say the data, or we could say the ages of GHC students in fall 2022 follow a normal distribution. Again, the idea that it follows implies that it's equal. The alternative then would be ages of GHC students in fall 2022 do not follow a normal distribution. Which is not equal or implies not equal. So our first step in any hypothesis test is to state our hypotheses. So we've done that. Step 2 in the process, if you'll recall, is to identify, I kind of call it the players. You have to identify your summarized data or the information that's given in the problem. Now, in this case, for calculating the test of normality, you need the raw data. And again, I provided the raw data in D2L. If you were doing this question, say on the quiz, they're going to give you the data. Okay, so you'll have to enter the data, or they may give you a data set to upload into Minitab, but you need the raw data. The third step is to determine which test to conduct. Now, at this point, we've only really talked about one, and we're only going to talk about one in terms of normality. So my only option here is to do the Anderson-Darling test for normality. That's the only one we're going to talk about with respect to determining whether a distribution is normal or not. So that's the only test I can run. Step 4 is we calculate and record the test statistic and its corresponding p-value. Now we do that using Minitab. Okay. So I'm going to go out to Minitab. I've already copied the data into the spreadsheet. We go to Stat, Basic Statistics, and then we scroll down to Normality Test. Stat, Basic Statistics, scroll down to Normality Test. I have to choose the variable. I'm doing age. Percentile lines, we choose none. Test for normality, we are doing Anderson-Darling. Then I'm going to click OK. And in the top half of my screen, we get a graph, and I'm going to copy that over to my paper. Okay, we get, basically it's called a probability plot of the ages of years, and it indicates that we're trying to determine if it is normal, if our data is normal. Okay, if it were normal, if you look at this red line, the way this particular graph is read, if you look at this particular line, your data points, which are represented by the blue dots, would tend to kind of curl or be located close to that particular line. Well, you can kind of see visually they don't really gather around that line. So visually it doesn't appear to be normal, but I can also verify that. Here off to the side, Minitab has calculated the mean of your data set, the standard deviation of the data set. It has the sample size, which was 46, and then it gives you AD, which stands for Anderson-Darling. So it gives you the test statistic for Anderson-Darling, which in this case is 0.7020. So I do have to write down that value for my test statistic. So my Anderson-Darling test statistic is 7.020. And then it also gives me the p-value for that particular test statistic. Now, notice here how it says less than 0.005. Minitab is telling you that's a pretty small number, that it's less than 5 thousandths of a point. Okay, for our purposes, we just ignore the less than. Okay, we just ignore the less than, and we're going to let the p-value equal 0.005. And both of those numbers come from the probability plot. Then step 5 is we make a decision to either reject the null or fail to reject the null by comparing the p-value and the level of significance, which Ms. Ralston forgot to put in the problem. Normally, that level of significance is given in the problem. Sometimes, though, so this is a good way for me to explain it, sometimes researchers leave off the level of significance so that the reader, who may also be a researcher, can decide what level of significance they want to use. Okay. And typically, if it's left off, we use a level of significance of 0.05. That's kind of the rule of thumb, the most popular level used. Remember, the level of significance is basically the probability that you make a wrong decision if the null hypothesis is true. So we're going to use alpha equals 0.05. So we've got to make a decision. Whoops. By comparing our p-value, which we calculated. Okay, so we're going to compare our p-value, which comes from Minitab, to the level of significance, which we're going to use the default level of significance, which is 0.05. So my level of significance is 0.05. My p-value was 0.005. Now, for whatever reason, from my experience, students struggle with comparing these decimals. I do not know why. The easiest way to compare them is to do it one digit at a time. So if I look at the first digit after the decimal in both values, I have a 0. So there's not really a way to compare it. In the second place after the decimal, for the p-value, I have a 0, and for the level of significance, I have a 5. I can compare those. I should know that 0 is less than 5. And since 0 is less than 5, that means that 0.005, the p-value, is less than 0.05, which is the level of significance. So my p-value is less than, the rule says less than or equal to the level of significance. And if you go back and look at our notes from Monday, or Tuesday, excuse me, if the p-value is less than or equal to the level of significance, we then reject the null hypothesis. The last step in this statistical process, or in the hypothesis testing process, is to write your conclusion. But to write your conclusion, you have to know or understand what it means when we reject the null hypothesis. Okay, so let me go back up here to our null hypothesis. Okay, so based on the evidence, we have rejected the null hypothesis. If we reject the null, that means the null is false or wrong for this particular problem. And therefore, by default, then, that means the alternative is true or correct. So because I rejected the null, that means the statement that the ages are normally distributed is false or wrong, and therefore by default the ages of GHC students do not follow a normal distribution. But I've got to say that in complete sentence form. So I would say preliminary analysis showed that the data, okay, let's make sure we're using the right words and go back up here. The data set for the ages of GHC students in fall 2022 is not normally distributed as assessed by an Anderson-Darling value of 7.020 with a p-value of 0.005. And there you go. Now, it looks like a lot of work. It really doesn't take that long to do the problem. Okay, I was very deliberate. I was writing out each step and offering explanations. So it doesn't necessarily take you, 15, 20 minutes to work through one problem once you understand the process. Questions before we look at a second example? Okay, so the second example says a local bank manager wants to know if the ages of loan applicants is normally distributed, and a sample of 30 loan applicants is provided. Now, I will say a normality test doesn't always have to do with ages. Okay, it just so happens that the two examples that I pulled have to do with age. So again, if you want to think about this formally, your question here would be, are the ages of loan applicants normally distributed? And so again, we begin our first step in the hypothesis test is to state the hypotheses. And I will point out for the normality test, we are stating those hypotheses in a sentence form. Sometimes we can use mathematical symbols rather than having to write out a sentence. But this one, we write out a sentence. So our null hypothesis would be that the ages of loan applicants follow a normal distribution. Again, that statement with that phrasing implies that it is equal, that it's equal to a normal distribution. The alternative hypothesis is the exact opposite, so it would be the ages of loan applicants do not follow a normal distribution, which again, that phrasing implies not equal. Now, I can go through it again, okay? Step 2 is to identify the players. Identify the information that you've been given in the problem. And again, for the normality test, what you're going to be given is the raw data. And again, I put the raw data in D2L. So if we go back to the D2L course, to the page for hypotheses, p-values, and normality, it says example 2, loan applicants. Okay, when I go to open this one, it is a .mtw file, which tells me it's a Minitab file. So I am going to save it, but remember, I'm not going to try to open it. I then go to Minitab, and I'm going to get me a new sheet. Then I have to upload or open that worksheet. MTW, W stands for worksheet, from my local file that I have saved on my desktop. It's loan applicant. And I click OK. And so again, I have the raw data. Looks like I've got information about income, education, age, residence, employment, savings, debt, credit cards, and so forth. Step 3 is to decide which test to conduct. Again, we are only doing one test related to normality. That one test is Anderson-Darling. So we're going to do the Anderson-Darling test for normality. Step 4, and again, when you're working through these problems, guys, you don't have to write these steps out. Again, I'm writing them for explanation so that hopefully you don't get lost when you go back to perhaps look at this video. So step 4 is we calculate and record the test statistic and its corresponding p-value. Okay, so again, we go out to Minitab to do that. So I'm going out to Minitab. It is Stat, Basic Statistics, scroll down to Normality Test. Again, I'm interested in age, no percentile lines. We are doing Anderson-Darling. And we click OK. And again, our plot, our graph with the information we need appears on our screen. Now, if you'll notice this one, in relationship to the first one, my points do seem a little bit closer or a little bit more aligned with the red line. Okay, so that might be a clue that this particular data set is normally distributed. Again, off to the side, you have your mean, your standard deviation, your sample size, and then you have your Anderson-Darling test statistic and the corresponding p-value. So my Anderson-Darling is 0.659. The corresponding p-value is 0.077. And again, I'm literally copying the information that's on the graph. Step 5 is we make a decision about whether we should reject or fail to reject, and we make that decision by comparing the p-value that we just calculated in Minitab and the level of significance. Now again, Ms. Ralston forgot to give us the level of significance, but again, typically if it's not given, we are going to use 0.05. So my p-value and my level of significance, I'm going to use 0.05, which is kind of the default rule of thumb if you don't know it, and my p-value is 0.077. Again, the easiest thing to do here is to compare digit for digit. So the first digit after the decimal is 0. The second digit after the decimal for the p-value is a 7. For the level of significance is a 5. 7 is greater than 5, so the p-value is greater than the level of significance. We are told if the p-value is greater than the level of significance, we fail to reject the null. Now again, we need to think about what that means. What does it mean to fail to reject the null? If we go back to our null and our alternative hypothesis, okay, to our null and our alternative hypothesis, we fail to reject the null, and if we fail to reject, that means that this statement is true or correct, and by default that means the other one would be false or wrong. So in this case, I have proven that it does follow a normal distribution. And so my final conclusion, which is the last step, okay, let me make sure I don't change colors. The last step in the process is to write the conclusion. And if we write the conclusion, we would write preliminary analysis showed that the data set for the ages of loan applicants is normally distributed as assessed by Anderson-Darling 0.659 with a p-value equal to 0.077. And there is your conclusion. Okay, so we've looked at two examples for normality. One in which you had a normal distribution and one in which you did not. Do you have questions? Jeannie, you got a question?
Yeah, I'm like trying to get it straight in my head. So this would really be like what we did in elementary stats was we assumed everything, like when we were doing the hypothesis testing, we kind of assumed that everything was normal. And so basically we're kind of going back and figuring out if our data is normal. And that would mean like we could run those parametric tests on the second set, but we shouldn't be running it on the first set, like the first one we looked at.
Right.
Okay, that makes a lot of sense. Thank you.
You're welcome. Naomi, do you have a question?
No, I don't.
Okay. All right. That gets you the material that's in the first lesson of module 3. Okay, that correlates to quiz 7. But quiz 7 is not due until the 16th of October. Your most immediate concern needs to be the midterm, which is due by Saturday, and then mini project 2, which is due on Monday and is related to confidence intervals. Okay, so I've kind of put this topic here on the back burner till you get through the midterm and mini project 2. I want to go ahead though, to kind of help us stay on track and maybe be just slightly ahead, and look at some examples. The next lesson in module 3 gets into looking at the 1 mean test, the 2 mean test, both of which are parametric, and then looking at the 2 non-parametric tests, which are Mann-Whitney and Wilcoxon. Cohen's D is a post hoc test that you can do after the t-test, and so we'll talk about it as well. So that's a lot of material. I've allotted 3 class periods to cover it, but I want to go ahead and look at some examples for the 1 mean test. I'm hoping that if you've had Stat 1401 in a recent semester, it will kind of be familiar to you. So we're going to look at, we've got about roughly 20 minutes. We maybe can get through 2 examples. I don't know if we'll be able to get through 2 or not, but we're going to look at specifically 1 mean Z test, or it could be a 1 mean T test. And if you'll recall, if you go back to the fill in the blank notes that we took on Tuesday, the primary difference between whether you use a Z test or a T test has to do with whether or not you know the population standard deviation. Remember, we use a Z test if we know the population standard deviation, which is sigma. We tend to use the 1 mean t-test when we know the sample standard deviation, which is S. Now, sometimes we also consider the sample size and whether or not we know the distribution is normally distributed. So again, in a lot of these questions, they may tell us to make that assumption. Again, in reality, we would do something like the Anderson-Darling test to verify that it is normal. Okay, so that's how you're going to make the distinction is, do you know the population standard deviation or do you not know the population standard deviation? So this first example says, a manufacturer of chocolate chips would like to know if its bag filling machine works correctly at the 438 gram setting. It is believed that the machine is underfilling the bags, thus cheating customers. 37 bags were sampled and found to have a mean of 435 grams. Assume the population standard deviation is 14. Use a 0.05 significance level, using a 0.05 significance level, determine if the bag filling machine is underfilling the bags. And guys, this is an example, and I don't know that any of you are studying in this field, but this is sort of an example, if you will, in the real world of quality control. Because if they're advertising that the bag has 438 grams in it, or if Coca-Cola is advertising that there's 16 ounces in a bottle, or Pepsi is saying there's 16 ounces in a bottle, they need to ensure that they are putting 16 ounces in the bottle or 438 grams of chocolate chips in the bag. Because as it says in the problem, if they're underfilling the bag, then as a customer, I'm getting cheated. If they're overfilling the bags, then they're kind of hurting themselves, because then they're putting more in the bag than they should, which can eventually cut into their profits. So you want to make sure that the equipment that you're filling it, and we allow for some deviation from the 438 gram setting. What if I'm at 437.6, or what if I'm at 438.2? Okay, we allow for some of that. Okay, but again, you want to make sure it's working right, so that you're not either cheating the customer or eventually going to lose profit because you're putting too much in the bag. So again, it's a good example of quality control. So if you think about it, the last statement usually in a lot of these scenarios are going to give you kind of the question or what you need to do, because it says determine if the bag filling machine is underfilling the bags. And I even went ahead, I added a little caveat. That means they're putting less than 438 grams in the bag. Okay, so when you read these scenarios that you're going to be seeing really in the course, and in reality, you would be the one saying, okay, I need to figure out, is it underfilling the bags and what that means? But I've told you that in this problem. So you want to look for, in case you're unfamiliar with it, you want to look for words like claim. This one uses determine. You might see believe, think, conclude. Usually you'll see maybe one of those words or a word that is synonymous with those, and that's going to help you to identify what your hypothesis is going to be. Okay, one of the hypotheses, whether it's the null hypothesis or the alternative hypothesis, will be given or stated in the scenario. Now, the challenge becomes you have to decide which scenario, which hypothesis do you have? Do you have the null hypothesis or the alternative hypothesis, because remember the first step in the hypothesis testing process is to state your hypotheses. Okay, so we need to be able to state our null hypothesis and our alternative hypothesis. And one of those has been given to me in the problem. And I have it highlighted there in green because, again, I found the word determine. And it says, is it underfilling the bags, or which means it is less than 438 grams. So if I see that word less than, that makes me think of the mathematical symbol that looks like this. And so then I have to think, well, would I use that symbol in the null hypothesis or the alternative? Remembering that the null hypothesis has to have an equal sign in some form. So this statement that we have here is going to be our alternative because it's less than. It doesn't say equal. So it's telling me that the mean amount in the bag is going to be less than the 438 grams that is required. The bag is being underfilled. From there, I can figure out what the null hypothesis should be because I know that the null hypothesis is the exact opposite of the null, or vice versa. So my null is going to be that the mean is greater than or equal to the 438 gram setting. There's my hypotheses. Then step 2 in the process is to identify the players. Identify that the information that you're given in the problem. Okay, so I know, at least initially, that the population mean is the 438 grams. Okay, your population mean is always the value that's in the hypothesis. So then I'm going to go back and read a little bit. 438, it is believed. Okay, it says 37 bags were sampled. So that tells me that my sample size, okay, and I'll make a note here. This is the population mean. Trying to give you all the details. Then it tells me that my sample size was 37 bags. That's N. It's almost like dissecting a sentence. And found to have a mean of 435 grams. Now, you have to be careful here, guys. You got to kind of, I don't know the proper English term, but read between the lines because it's talking about the 37 bags that were sampled, and those 37 bags had a mean of 435 grams. So that 435 grams refers to your sample mean. So the sample mean for those 35 bags was 435 grams. And lastly, it says, assume the population standard deviation is 14. And it does say population standard deviation, which is sigma. That's my population standard deviation. Now, it doesn't matter the order in which I list these. It also then says using a level of significance of 0.05. Now, the level of significance here is 0.05. If my level of significance is 0.05 or 5%, remember that means that my confidence level is 95%. Okay, remember the two, they're connected together and they have to total to 1. Now again, the order in which we list those doesn't matter. I kind of listed them in the order in which I found them in the problem. Based on the information that I have identified in the problem, then I'm going to do step 3, which is decide which test to conduct. And right now, your options are Anderson-Darling test for normality, the one mean z-test, or the one mean t-test, because those are the only ones that we've really even touched on. Well, if I look at this problem and I notice that I have the population standard deviation. When I know the population standard deviation, that means I'm going to do a one mean z test. Now, remember that the one mean z test is connected to or related to the normal distribution. And if I go back up here and look, it doesn't really tell me anywhere in the problem to assume that I have a normal distribution. But notice that my sample size is over 30. So regardless of what the distribution is, I can use the central limit theorem and kind of force it to be normal. So I'm okay there. I don't have the information in this problem. We're going to have to make the assumption like we did previously in Stat 1401, because this is a topic from 1401, that we have a normal distribution. So then step 4, we're going to calculate and record the test statistic and its p-value. Okay. So these are some new steps, but the steps are available in D2L. Remember, I have the steps in the folder Minitab instructions. And we'll be doing some more of these because I'm probably only going to get through this one. We'll look at some more of these next week. Okay, so here's how we do it. We go to, I hope I can remember, graph, probability distribution plot. Nope, I think I'm wrong. Hold on. Sorry. Stat, basic statistics, one sample Z. We have summarized data. Our sample size was 37. My sample mean was 435. The known population standard deviation is 14. We are going to conduct a hypothesis test. My hypothesized mean is the 438. I then go to options. My significance level was 0.05, which means my confidence level is 95. And then I have to choose the symbol in the alternative hypothesis. We were looking at less than. So I'm going to change it to less than. Okay, Don't get too caught up today because we're getting short on time. We'll look at some more examples. Okay, but we choose less than. I click OK. I click OK again, and it comes up, and I get a variety of information. Okay, they give you some descriptive statistics, but then I also scroll down and it gives me the test. Okay, so I need the piece that's got the header for test, because under that header it gives me my Z value. Okay, so here is my test statistic. Okay, so my Z is negative 1.30, and then it gives me the corresponding p-value, which is 0.096. Okay, so from that printout, I can read my Z test statistic and its corresponding p-value. Then I move on to step 5, which is where we're going to make a decision. Remember, we make a decision by comparing the p-value to the level of significance. So in this case, I need to compare the p-value, which was 0.096, to the level of significance, which was 0.05. That was given in the problem. Again, the easiest way to do that, guys, is digit for digit. 0 compared to 0, 9 compared to 5. 9 is greater than 5, so the p-value is greater than the level of significance. When the p-value is greater than the level of significance, we fail to reject the null. And then the last step is to write your conclusion. Your conclusion should always include the level of significance. You can usually, I either tag it at the beginning or at the end. So I'm going to write it at the beginning here. At the 0.05 level of significance. And then I've got to write my conclusion, but I got to figure out what my conclusion should be. So we have, based on the evidence we have failed to reject the null. So if I come back up here to the top and I have said I'm going to fail to reject the null. If I fail to reject, that means the null is true, and by default the alternative is false. So I've got to write my conclusion such that it indicates that I'm putting either exactly 438 grams or a little bit more, because I have failed to reject the null. There's a variety of ways you can say it. If I use this same statement that was in my problem, I could say at the 0.05 level of significance, the bag filling machine is not underfilling the bags at the 438 gram setting. Okay, that we were trying to determine if it was underfilling the bags. We determined that it is not, which is what I said. The bag filling machine is not underfilling the bags at the 438 gram setting. Now, guys, there's lots of ways to say that sentence. We could say the bag filling machine is overfilling the bags. We could say the bag filling machine is putting at least 438 grams in the bag. I mean, there's lots of ways to say it, but you have to say it in such a way to indicate that that null hypothesis is true, however you say it. Now, hopefully that process and even that question, that process of hypothesis testing for a one mean Z looks familiar. I hope it does, because that's something you learned in 1401. Again, it may be a while since you've had that, so that was a nice little review, but we may have to do some more of those as we get into hypothesis testing. And guys, we're going to be doing hypothesis testing pretty much for the rest of the semester, just so you know.